Welcome back, learners! In this video, we're going to learn how to do basic integration. Say we are presented this. We will integrate this thing. We read this as the integral x raised to 4 minus 8x cubed plus 3x squared plus x plus 5 with respect to x. Or the antiderivative of x raised to 4 minus 8x cubed plus 3x squared plus x plus 5 with respect to x. This wormy symbol that you see is the integration symbol. So when you see that, that means you are solving an integration problem. But what is integration? It is actually the reverse of differentiation. Now, to answer this example problem, we'll be needing some basic integration rules. First is the power rule that says that the integral x raised to n with respect to x is equal to x raised to n plus 1 over n plus 1, and then the plus c. That is very important. And in this rule also, n must not be equal to negative 1. Now, why do we have the plus c? How important is this? Let's consider x cubed as our example. What is the derivative of this x cubed with respect to x? Following the rules, we know that the derivative is 3x squared, right? And since the derivative is the opposite of integration and vice versa, we say that the integral 3x squared should be equal to x cubed. But what if we get the derivative of, say, x cubed plus 5 with respect to x? Again, based on the rules, the derivative of this is 3x squared also, because the plus 5, which is a constant, has a derivative of 0. And also, if we get the derivative of x cubed minus 10 with respect to x, the derivative will also be 3x squared, right? Because the negative 10 is a constant that has a derivative of 0. Now, if we say that the integral 3x squared with respect to x is having the answer x cubed, just x cubed, what will or how can we justify these parts here? Right? So that's where the plus c is important. We add a c here, which is our placeholder for the constant, because we are not sure if there is a constant and what is that constant. So it's very important that in your final answer in integration, you have the plus c at the end. Another rule that we will use to answer this problem here is the constant rule that says that the integral k with respect to x is equal to kx plus c. This constant rule can be proved using this power rule above, thinking that beside k we have an x raised to a 0. Or you can just find the derivative of this. The derivative of kx is a k, just a k, right? And c a constant, the derivative is a 0. So the derivative of kx plus c is just a k, which is this one. Another rule that can help us solve this sample problem is the constant multiple rule. It says that the integral kx raised to n dx is just equal to k integral x raised to n dx. Another is the sum and difference rule, where we just find the integral of each term in the sum or difference of terms. Now let's proceed to solving our sample problem. Applying first the sum difference rule, so this is the same as finding the integral x raised to 4 dx minus the integral 8x cubed dx plus the integral 3x squared dx plus the integral x dx plus the integral 5 dx. Now let's apply the appropriate rules for this. we have equals. So for this first one, we will apply the power rule. So it will be x raised to 4 plus 1 over 4 plus 1. And we're supposed to write plus c, right? But since every integral here will have a plus c, we'll just put that plus c at the end. Because after all, if you combine all the c's, it will still be a constant. Okay, so let's proceed to the second one. We apply the constant multiple. So this is minus 8 integral x cubed dx plus, same as this third one, factor out the 3, then integral x squared dx plus, for this next one, let's apply the power rule again. So we can, we have an implied 1 there as an exponent, right? So x raised to 1 plus 1 over 1 plus 1. And for this last term, we'll apply the constant rule where the derivative, the integral 5 dx will be equal to plus 5x. And there we put our plus c, only at the very end. Let's go to simplifying this. We have equals, we have x raised to 5 over 5. Then we have minus 8, and we apply the power rule here. X raised to 3 plus 1. Let's just do this step by step. 3 plus 1 over 3 plus 1. And then plus 3. Again, power rule here. So we have x raised to 2 plus 1 over 2 plus 1. There. And this one we can simplify already. X squared, right, over 2. And just copy the remaining parts, plus 5x plus c. And then simplifying further, we have x raised to 5 over 5 minus 8. And then for this one, we have x raised to 4 over 4. And then our plus 3, and then this will be x cubed over 3 plus x squared over 2, and again plus 5x plus c. And then simplifying, x raised to 5 over 5, this can be cancelled, right? So we'll have only minus 2x raised to 4. Cancel this one, so we have plus x cubed plus x squared over 2 plus 5x plus c. And this could be our final answer already. Now let us have examples that involve negative powers. Let us have the integral x raised to negative 5 with respect to x. We can actually just apply the power rule here. So this will equal x raised to negative 5 plus 1 over negative 5 plus 1 plus c, of course. And it will give us x raised to negative 4 over negative 4 plus c. And since the negative powers and answer, we have to fix that. So it will be negative 1 over 4x raised to a positive 4. And then the plus c, of course. For another example, let us have the integral 1 over x cubed dx. So this can be rewritten as x raised to negative 3 dx. So the integral x raised to negative 3 dx. So we just apply again the power rule. So this equals x raised to negative 3 plus 1 over negative 3 plus 1 plus rc. And then simplifying, we get x raised to negative 2 over negative 2 plus c. And again, fixing this without negative exponent. And transferring this, the negative sign at the middle to signify finality. So we have negative 1 over 2x raised to a positive 2 this time. But what if what we have is the integral x raised to negative 1 dx, which is the same as the integral 1 over x dx, right? Can we apply the power rule here? Because what will happen if we apply the power rule? We'll have x raised to negative 1 plus 1. We know what that is, right? Negative 1 plus 1 plus c. This negative 1 plus 1 is a 0, right? So x raised to 0 over 0. So what is this thing, right? So the power rule cannot be applied to this kind of example or problem. Which leads us to another rule when n is equal to negative 1. It says that the integral x raised to negative 1 dx is equal to ln absolute value of x plus c. An example of this is when we integrate the integral 1 over 5x dx. So we can rewrite this as 1/5 x raised to negative 1 dx, right? And applying the constant multiple, we can factor out the constant 1/5. So we'll have 1/5 integral x raised to negative 1 dx. And then applying the rule, we have 1/5. So we'll have ln x and then the plus c here. And finally, we have 1/5 ln absolute value of x plus ac. Just a c. Even if we distribute the 1/5 c will still be a constant, right? So we can just write that as c. Now let's have examples that contain or may contain fractional exponent. First, let's have the integral x raised to 3/4 dx. So applying the power rule, we have x raised to 3/4 plus 1 over 3/4 plus 1 plus c. Therefore, we have x raised to 7/4 over 7/4 plus c. And we simplify this as 4x raised to 7/4 over 7 plus c. Next, let's have the integral 1 over x square root of x dx. Let us write this into a simpler version slowly. So we can rewrite the radical part as 1 with fractional exponent, right? So 1 over then x by x raised to 1/2 dx. And then simplifying the denominator, multiplying same base, we add the exponents. So we have here an implied exponent of 1, right? So it will be x raised to 1 plus 1/2, that's 3/2, okay, dx. And then we can transfer this to the numerator, right? Giving us with x raised to negative 3/2 dx. And now it's easier to integrate, right? We can now apply the power rule. We have x raised to negative 3/2 plus 1 still over negative 3/2 plus 1 and the plus c. And then simplifying this further, we have x raised to negative 1/2 over negative 1/2 plus c, and as our final answer, we have negative 2 over x raised to positive 1/2 plus c. Or you can bring back the radical if you want. This could be negative 2 over square root of x plus c. Another example, let us have the integral x plus 5 all over square root of x dx. We can actually transform this first before integrating. We can write this as x raised to 1/2 and transferring it to the numerator and distributing it to x and to 5. So let's do that first. So we have the integral x plus 5 over x raised to 1/2 dx. And then this becomes the integral x plus 5 multiplied by the transferred x raised to 1/2. The 1/2 becomes negative this time. Then dx equals, now we distribute these two terms here. Then we have the integral. We multiply same base, apply addition on the exponents. So x raised to, that's an implied exponent of 1 there. So 1 plus negative 1/2 is just a 1/2, right? And then we have 5x raised to negative 1/2 dx. Now it's easier to find the integration, right? Another way is to separate the numerators and divide each by the same denominator. Like we'll have x over square root of x plus 5 over square root of x dx, right? Now let's do that. We'll have the integral x over square root of x plus 5 over square root of x dx. And then simplifying this, we have x over x raised to 1/2 plus 5 over x raised to 1/2 dx. And simplifying further, we divide the same base. So apply subtraction on the exponents, right? Again, the implied 1 here. 1 minus 1/2 is a positive 1/2. So we'll have x raised to positive 1/2 plus transferring this part here, this x raised to 1/2 here to the numerator. Then we'll have 5x raised to negative 1/2 dx. Well, actually, they are the same. This one to this one, these two are the same. But as you can see, it's easier now to get the integration. So let's now proceed to the integration of this given example. Since we are applying the integration rules now, we will drop this wormy symbol here. So we have x raised to 1/2 plus 1 over 1/2 plus 1 plus 5x raised to negative 1/2 plus 1 over negative 1/2 plus 1 plus c, of course. And then simplifying this further, we have x raised to 3/2 over 3/2 plus 5x raised to 1/2 over 1/2 plus c. And finally, we have 2x raised to 3/2 over 3 plus the 2 will be multiplied by the existing 5 there, so that's 10x raised to 1/2 plus c. But if you want to bring back the radical, since the original given has a radical, you can actually do so. We can just write this as 2. Since 3/2 is bigger than the denominator 2, we can write that as 2x times x raised to 1/2, right? Because if we multiply this x by x raised to 1/2, that's x raised to 3/2. So all over 3 plus 10x raised to 1/2 plus c. And finally, we'll have 2x, x raised to 1/2 is square root of x. And all over 3 plus 10 square root of x plus c. This could also be your final answer. Okay, another example. Let us have the integral x plus 2 multiplied by 3x minus 1. One thing you should know, there is no product rule for integration. There's another technique that we can actually use, but it will be discussed in another video. So for this type of problem, what we can do is to really multiply these two binomials here. So we do foiling, right? So it will be the integral 3x squared minus x plus 6x minus 2 dx. And of course, we combine like terms. So this is the integral 3x squared plus 5x minus 2 dx. And then we just apply the integration rules, sum and difference, all that, constant multiple, power, and then constant to really get the integral of this. So let's apply those rules. Drop the wormy sign or symbol. We have 3 and then x raised to 2 plus 1 over 2 plus 1 plus 5x raised to 1 plus 1. Remember, there is an implied 1 there. Over 1 plus 1. And for the constant 2, we have minus 2x, like that. And of course, the plus c. Let us not forget that. Then we have as a simplified version, so 3x raised to 3, not yet simplified because we'll be canceling out some things later. And then 5x squared over 2 minus 2x plus c. And this time, finally, cancel this. So we'll have x cubed plus 5 halves x squared minus 2x plus c. Now let us have the integration rules for trigonometric functions. Example that involves trigonometric functions. Let's have the integral 6 cosine x plus 5 sine x dx. Applying the sum rule, we can have this as the integral 6 cosine x dx plus the integral 5 sine x dx. Right? And then applying the constant multiple rule, we have 6 integral cosine x dx plus 5 integral sine x dx. And then we have 6 and then the integral cosine x dx according to the rule should be sine x plus c, right? But we will not put the plus c anymore, only once at the end of this answer to the integration. And then plus 5, so the integral sine x dx is negative cosine x plus c. So again, the plus c is here at the end. For the simplifying, we have 6 sine x plus, it becomes negative now because of the multiplying by negative cosine x. So it will be minus 5 cosine x. And then the plus c. Now let's have the integration rules for the natural exponential functions. Observe that here we see that integration is indeed the reverse of the derivatives, right? Because here we multiply e raised to g of x by g prime of x, but we unmultiply for the integration. E raised to g of x over g prime of x. So division this time here. And now for an example that involves natural exponential function, let's have the integral e raised to 7x plus 5 dx. So, applying the rule, this is just equal to the given exponential term itself, e raised to 7x plus 5 over the derivative of the exponent plus c. And then let's simplify this. Apply the differentiation. So we have e raised to 7x plus 5. The derivative of 7x plus 5, it's just a 7. So that's it. That's our final answer. Or we can write this as 1/7 e raised to 7x plus 5 plus c. So learners, what would you like to learn next? Comment below.